you really want to watch it, you're going to stick around, see what happens. That's us. Cool, that is not us. Still the wrong folder. There we are. Alrighty, friends, let's just take a minute to come into this room and let's do a reset. So, yes, laptops, please. Let's just close them. There'll be plenty of time for working. Thank you, Vine. Take a minute to just settle in and see what happens. Mainly if you can just let go of whatever was entangling your thoughts. No idea what happened there for you. Probably some weird shit. That's what happened for me. All right. So, any questions, my friends? Anything you want to talk about? I got stuff to talk about. Hopefully, right? I should have called off class if I didn't. Anybody got anything they are concerned about? Take that as a no. So we are going to talk about numerical solutions today. Oh, actually, hey, quick warm-up. Just pretend, fake quiz to reinforce some things. Here's a phase diagram. So here's x dot, here's x, and this, and so that's 2, and that's minus 2. And we are looking at the phase diagram for that autonomous DE. And so could you just please answer, using that, answer these questions. If x at 3 equals -4, what is the limit as t goes to infinity of x of t? And let's do that for at least one other initial condition. I put a little bit of a trickiness in there. Can we just take a moment on that, please? And we'll come together. Did you get your glasses, or you just wear them for the first time?
No, I get them when I have headaches, so.
Oh gosh,
Yeah.
okay, I'm sorry you
No,
have a
you're
headache.
fine,
Yeah,
you're
yeah.
fine.
But they look great.
Thanks.
They're very
I'll take
nice.
it.
If only a compliment could drive a headache away.
That helped.
Oh, cool. Okay. Y'all started online service. get too fancy. One day we'll have an exam or something. This will be a question on the exam. Not this one, you know, but if you could do this, you're getting what's been going on. So let's check in together. Give this phase diagram. This is, you could think of this as the velocity versus position graph. And phase just meaning state diagram. It tells me the relationship between position and velocity. But time is hidden. I don't know time at all. There's no time flow in this diagram whatsoever. But I can indicate how time would flow. If I just look at the actual position line. So if I just pull down, and this is just x, this helps me gauge what's gonna happen down here. But notice that this means, and I had a couple of folks asking me questions about this, so that's why I wanted to review this. Here the velocity is negative in this window. Here the velocity is also negative. And that means x is decreasing, and that's in this window. So negative, negative, it sometimes switches like it will here, where the velocity is positive on the other side of that equilibrium point. But when I put this all together, and you can make these marks up there or on a separate line, I just wanted to pull it down because we can just look at this and tell everything we need. And so I'm just marking the arrows, and these are my equilibria. So let's talk a little bit about terminology from the book. This is an unstable equilibrium. So, or sometimes, I think like our book uses node for a very specific thing, but this is an I'll just say unstable equilibrium or a source node. You can think of this as things emanating from it, like there's a little hole in the ground and water's pouring out, moving left and right. So things are sourcing from there. Over here, we have what's called a half stable, and so that means half unstable equilibrium. Because if I veer to this side, the current pushes me back, but if I veer to this side, all is lost, and we just travel to negative infinity. So, any questions on that before I go on? Does that make sense? Yes, Lou?
The two arrows pointed to the same point, that would be a stable one.
Absolutely, yeah, that would be a stable equilibrium. We don't have that here, but yeah, absolutely. Yes?
What does the book call a stable equilibrium?
Sync, sorry, sync. Yeah, that was what I was, because it's not on here, so I should have put one on here. But a stable equilibrium where you have something like this, when you have flows into it, a stable equilibrium is a sync. Things are being drawn into it. Those are great questions. Thank you. Other thoughts, questions? Cool. And then from this, you should hopefully be able to sketch an actual direction field in the solution space. Notice we have t versus x here. We've got all these different spaces floating around. So that's what this homework was about, getting those straight. So I mark off my equilibria. I know that if I am ever at x equals 2, I still have to answer those questions. If I'm ever at x equals 2 or x equals minus 2, I never leave there. You cannot get to an equilibrium if you're not on it at some point. You can get closer to it, but you can't ever get on it. The only way to be at equilibrium is to start at equilibrium. So really important thing to remember. And then I mark these through, so if x is less than -2, I flow downward. I've got negative slope down there. We're also negative slope in between these two bands, and so remember that you always leave an equilibrium asymptotically and approach equilibria asymptotically. So my flow must look like that inside there, and then up here we just keep blowing up. And so that makes that cake to answer. And usually I give the initial time as 0. I just wanted to twist it up, throw some extra numbers in there. If x is equal to -4 at any point, at any time, that means x is out here. So here's -4 out here. X just keeps decreasing. If x is -4, that's here. X just keeps decreasing. So this answer is going to be -infinity. It just keeps on, it never bottoms out, it just keeps dropping forever. However, if x, the x coordinate is 0 at some point, say like right here, I flow toward -2. You can see that here. If x at 0 is 3, x at 3 is 0, got it, that's backwards. I was tricking myself. Then I just head toward -2. That's all stuff we can answer without even solving the differential equation, whatever it is. We don't even know. We could make up one, but we're not going to. Questions on that? We all good? It's a good little review. Awesome. So these curves that I'm drawing in here, I want to talk today about how the D-field program that we have been using sketches those curves. So let's talk about numerical methods in differential equations. We're going to just scratch the surface. We're going to talk about the most fundamentally basic one, which was the very first one ever created by Euler, math god Euler. And then what came a little bit better later is an improved version. So we're going to talk today about Euler's method. And then we're going to talk about improved Euler's method. And I had fun last night just playing with spreadsheets. So I made us a nice little spreadsheet that I'm going to share with you. And we're going to look at it. You can go have fun with it too, because spreadsheets are awesome. And doing math in a spreadsheet is pure joy. After dinner last night, Amy was going up to, my wife is a lawyer. She went up to her office to do more work, because lawyer's work is never done. Professor's work, I don't know, comes and goes. But yeah, she came down, she's like, what are you doing? I was just having fun after dinner, spreadsheet. That's recreation. That's like a video game, right? That is essentially a video game. The best kind of video game. You're making that shit. So improved, and this should say Euler's method. I was too enthralled with my own story there. Improved Euler's method. These are all part of a collection of methods called Runge-Kutta methods. And I'll explain to you what some of the more advanced ones are, but once you understand improved Euler's, you really understand them all. They're just more involved versions of this. And this pen is no good anymore. So, let's talk about Euler's method. It's very intuitive. And just what's so cool is just how intuitive it is. I don't know if Euler was the first person to ever think about this, but he got his name on it. So let's say we're given an initial value problem. Let's say x dot equals f of tx. So that's not necessarily autonomous. The slope could change with t. So I don't see those bands across necessarily. I only see those bands of solutions with constant slope when I just have an autonomous. And an initial condition. So let's just say x at some time equals some value. And let's draw a picture. So here's t naught. Here's x naught. There's our point. That is definitely on our solution. That's where we're starting. So the first thing you do is follow the direction field at that point. Remember how these D fields are just a bunch of slope lines all over the plane. And right here, there is a current. So the thing I'm going to do is find the slope of this line. And the slope of this line is given by this formula. So the slope is equal to f at t naught, x naught. Just whatever that function is. I plug point coordinates in, and I get my slope out. So we'll call that, yeah, we'll just leave it like that. Now, the thing that I have to determine is how precise and accurate I want this, which are two different things, but how precise I want my solution to be. So I have to decide how far I'm going to step to find the next location we're approximating. Computers can't do continuous things. I mean, more or less they can. So I can't just like sketch a curve out here. I have to pick the next point and figure out where would I be if I just followed the current at this point for this long. So we're going to set a time step or an independent variable step of delta t, and that means this distance here is delta t, and my next point is my initial point plus delta t. And I come up to here, and what I want to know is, what is that coordinate? If I pretend like this doesn't change between here and here, I look at the slope here, I follow the line with that slope up to here, how high up am I? That's all we have to do, and that's Euler's method. Repeat. Then Euler says, okay, now here, start over. Here's your new information. Get the current slope there. Follow that slope. Delta t units to the right. Where do you end up? So let's write out the algorithm. And actually, let's just put the point here. So this height here, so new height, or new x coordinate, is going to equal my old x coordinate plus the slope at this point times delta x. This is your slope. This is rise over run. So if we multiply it by run, we get the rise that's associated with that. And repeat. So let's write this on all up. So our basic algorithm is this. So let t sub k, x sub k be our current point. And when k equals 0, that's our initial point that we're given. You have to be given that, otherwise you don't know how to do any of this Euler stuff. So the next t value, t sub k plus 1, so this is my next t, is equal to the old t plus the step size, which is fixed. And that's always going to change. That's never going to change for us the way we do it. There are adaptive methods that change the step size if things start looking funky, but that's basically for a whole other class called numerical methods, which I'm teaching this fall. So if you like this, and you like math and computers, that's the class for you. So we update our time, and then we update our position, our vertical position. So xk plus 1 equals the old xk, so this is next x value, plus current slope times delta t. That's it. Repeat until you get where you want. You get to the desired t value. That's it. Let's just do one by hand really quick. And then I'll pull out my, yeah, we'll do one by hand. Okay, let's just do one by hand. So, because you really should do this a couple of times by hand. It's neat that we can. So let's say x dot equals t times x. And that's going to be an example that I have in the spreadsheet. So we'll do it here and then just see how it all. Yes, sorry.
So should it be delta t up there as well?
Thank you. Yes. Yes, please change that to delta t. Thanks, Gwen. Okay, thanks. Yes. Good. Good call, because there it is right there. Luckily I got it. And then we have x of 0 equals 1. So we'll make out a little table. Sometimes it's nice to have a table for this, just to keep track of sanity and so forth. So here we're going to put f of tx, and then here I'm going to put x plus f of tx delta t. So this right here, this is going to be our slope. And then this is going to be our updated output x value. We've got a pretty chill thing, so let's together just start this, or if you just want to start cranking on it, please go ahead. But remember that f of tx is this guy. And it says multiply the x coordinate and the t coordinate together. Yay, that's sweet. And we should set a delta t, we're gonna need that. Let's just do 0.1, the 10th. So over here, I'm gonna take my current x plus my slope at this point, which is 0 times 0.1, it's just 1. So that's my next x value. Let's plot these as we go along. So this is x, and this is t. We are starting here, let's say that's 1 right there. And then I go over a 10th. So initial condition, and now I'm still at 1. So my first curve, I could just put dots here, but the computer would connect those with a line. You can see how inaccurate this already is, because there's actually flow going up here, but this thing is pretending like this is all just constant across here. So now our new point is 0.1. I'm going to add the delta t to get to the new delta t, and I'm going to copy this one down, my current x value. So could you take this a couple more turns, please? Just yeah, crank a couple more iterations of that out while I go get my spreadsheet going here. Get to the improved version. Start giving some sanity checks, or getting them, as the case may be. So this is that right? Wait. Yeah, I guess so. Just a very small increase. Is that what we got for our next increase? 1 in 1,000th? Okay, cool. Is there any questions on how I got that? Because let's fix it now. Maybe I yeah, because I can't multiply a 10th times a 10th, so I like your answer better, Boyd, thanks. Thanks for being always vigilant. That sounds better. Boy, that sounded a little crazy. So I think Lou's nodded, and we both had a little zero if you're looking at that, yeah. Good company, we're in good company. All right, so that looks good, and so now I just keep doing this. That times that is going to be 0.202, I believe. And then when I take my current value, 1.01, plus this value, times 0.1, oh, that's not gonna be so bad. That's just 1.01 plus 0.0202 equals 1.0302. And that is my next, that is our approximation for the solution at 0.3. I'll stop. Yeah, Lou.
So is that supposed to like take that like one box you just did?
I'm sorry, this box here?
Yeah.
Yeah.
So those individual lines are just like increments, stuff like
Yes.
it's not like then you times that.
Yeah, correct, yes. So the steps are just in these individual columns, and there's just a lot of computation in that one. I was just literally simplifying out that part right there. Is that what you're asking?
Yeah.
Okay. Any other troubles with this? Let's take a look at the actual solution. So actually, let's plot this out just a little bit. My scale is going to be hella hard to work with here because this is 1. I don't even know how to do 100th. I think this pen is wider than 100th of that, but we'll just pretend. So over at 0.2, I've got 1.01, so we went up a little. I'll put the numbers right above, so at least there's some kind of indication of what the hell's going on. And then at 0.3, we went up a little bit more, but still not a lot. But so I'm gonna make it look like more, but boy, don't trust these slopes. But it's something like that. That's our solution. So if I went to the D field thing and I clicked right here, I'd see a nice smooth curve coming out. And we'll talk about how to make that a better curve very soon here. But here's the actual solution to that problem. So the true solution to that initial value problem is e to the 1/2 t squared. And you could prove that to yourself pretty readily. And actually, let's prove it to ourselves. Notice that here's the check. X dot, the derivative, is e to the 1/2 t squared times the derivative of the exponent, which is just t. Notice that x dot is equal to x times t. That's just x again. And certainly when I put in 0 here, I get 1 out. So we've got x is 0 equals 1, check, and then, yeah, it's got the right rhythm. Just to remember what it means to solve a differential equation with an actual formula. So this thing here, I'm gonna need some help. Let's do the true solution over here. So in other words, what is the value of that when t is 0? Well, we know it's 1. Could someone please compute this value for us? So I have it in my spreadsheet, but if someone could do that for us, that would be peachy keen. And we'll see how far off that number is there. Most certainly won't do that in my head.
It's like about 1.005.
So like this?
Yeah.
Yeah, anybody else getting something like that? Yeah, cool, awesome. So the truth is actually a little below where we're at, right? So the true value is right there. And could someone do this one then? Oh wait, shit. No, that's here, isn't it? Yeah, true value's above. That was where it was supposed to be. So here's the true value, which is 1.005-ish. Could someone just give me the true value here at 0.2, please? So in other words, this quantity.
1.02.
1.02, thank you. So come up here, and 1.02 is the truth here. And I'm putting equals even though I'm gonna say approximately 1.02. So we are way under the truth, actually. Significantly. Depending on what this is modeling, that could be a lot. And anytime you're doing science, a 1/100th is a lot. You don't want to be off by that much. So this is okay. It's giving us a good feel. What could I do to this just without knowing anything else to make that a better approximation? What can we do here? What can we alter in the, yeah, Katrina?
Make your time step smaller.
Yeah, beautiful. That's the calc answer, right? In calculus, if you don't like your answer, make the rectangle smaller. Make the plus h smaller. Oh, I thought you had to. I thought that was all good, Tracy. Yeah. So to get a better approximation, you can decrease the time step if we decrease delta t. So that's always an option. But then you have more steps to do to get up to where you were. So if I decrease the time step to 0.01, for example, there's going to be 10 steps in between each of these. Just to get from here to here is 10 different computations. And if it gets smaller, even worse. So let's find a way that we can make things better without altering our timestamp, our time step. And that is improved Euler's method. It's really cool. It's the tiniest improvement we can make besides decreasing our time step. This is a whole new method. So here's the plan. We're going to start off again, T naught, X naught. We're going to actually do Euler's method from this point. So I'm going to move over T naught plus delta t, and I'm going to do Euler's to get this next approximation. So for this one is do an Euler's method, just as we talked about, approx for the next output value. So step one is do Euler's method. Record that. So I'm going to write that down. So at this point, so this first guess should be, let's see, so we're going to have x, our current x value, plus f at t naught x naught delta t. And again, let me put this up so that we have everything notated carefully. Same problem we had before. So I'm going to find that. Then I'm going to find the slope at this point. So I'm going to move into the future, find the current at this point. So like right here, here was the current that took me there. Then I'm going to grab the current here, and I'm going to use that as part of my new slope information. So I'm going to average these two slopes together. So I'm going to reach into the future, grab the slope there, average that with my current slope, and use that as my direction to head off from where I'm at. So do an approximation, grab the slope here. So what is that going to be? That slope is going to be f at t plus delta t. I've got a t naught plus delta t, comma, this whole value. So it starts to look very cumbersome. So this is the future slope. And average the two slopes we know. We now know. So here's our update. The update is going to look like this. I'm going to take my original, so x1 is going to equal x sub 0 plus 1/2 average slope. So current slope is where I'm at, plus future slope and you start writing this shit. Like this is good stuff to show your friends who aren't in math. Say, totally understand this. Makes a great deal of sense to me. Ooh, don't put that delta t there. Oh no, do put that delta t there. And then out here we put a delta t for our average slope. So this thing right here is our average slope. And that gets us a better approximation because it's taking more information in. So like, I'm happy to help translate any of that there. But I am going to pull out a spreadsheet to do this because we ain't doing this by hand. Kind of, okay, sure. That's where you want to stop. So this spreadsheet is available to you. See what happens. So far, so good. Less good. I'm gonna wait a second instead of spazzing out and start pushing buttons. Yes! Huzzah! All right, spreadsheet. So up here in this little box, I've set my, so this isn't x's and y's, so I apologize for that, but it's the same stuff. dx will be my step size, so that's the delta x. And you can't see the problem that I'm solving here, but it was this one that we already did. So here's the differential equation that I'm solving there. So what I did, and let's go through this, was initialize when x is 0, y is 1. And there's nothing after that. The way this thing feeds is it's going to kind of grab back to the previous state to get the next state. So let's go through these cells. And let me show you what's up here. So first thing, after I initialize it to just 0, notice that you can look in this top bar if you're not used to looking at spreadsheets and see what it is that I'm entering in that cell. The next one is just A4, so the previous cell plus $A, $2, that is actually locking the reference to this cell. So if I copy this and paste it down, it'll adjust this one, but it won't adjust this one, because I always want it to point back to here, so that's a static reference if you're a programmer, or if that even makes any sense. Static makes sense, right? Staying still. And then I just kind of copied that down. So here's the classic move. This is gonna screw this all up, but it's okay, I can put it back. So just take this and grab this little bar and move all the way down, and it's super smart. And it just fills things. And that's why Excel's so damn fun to use. One of the reasons. So then in this next step here, let's see, what do I got there? So that is actually updating to this value over here. But basically what I have in column B is a copy of column F, my final answer. So how do I get there? Well, here is f of x, y. That's this thing here. So for us, this looks like this. Y at x naught is y naught. Notice how it's just multiplying the x value in cell 5 times the y value in cell B5. So A5 times B5. Oops, sorry, A4 times B4. I'm going back to this one. So it's 0 times 1. And then the next one, this is my Euler update. So I'm taking my current y value, which is this one, plus C5, whatever that slope is I computed, times my dx, my time step. And I've got that with dollar signs on it, so it doesn't move either. And then right here, I evaluate the function, this thing here, at my new point. So what is my new point? It is, let's see, what do we got here? So we got A4 plus 0.1. So I'm taking this, I'm moving it, I'm adding 1 to it to get to my next time step. I could have probably pointed here, that would have been fine. Times D5, my predicted slope out in the future. All right? So that is the future step. And then in this one, I average those two, and you can actually average those yourself. So I take that plus that divided by 2, I get whoa. Oh, okay. And then I multiply by the time step. Yep, so it's all good. So that is this right here in that column. And that's about it. And then I just did this all the way down. So let me clear it out so we can just see that fun together, because it's just so easy and so beautiful. I hold shift, select all those, and I just pull down and boom. Thanks. So cool, right? Like, damn. Imagine having to do this by hand. What a nightmare. So we're seeing in this column, this is actually the normal Euler's approximation roughly here. It's a little tweaked because these y values are getting tweaked, but this is kind of the standard Euler's method. Over here in this column, I have what we expect to be the true value. So you can compare it right to over here. This is the approximate value. Here's the true value. Pretty good. Remember now, this is the improved Euler's. That's a hell of amazing. It's got an absolute error that's very small and a relative error that's also very small. As we keep going down, we see the error. Well, here's the curves. If I wanted to plot these, I could plot this times this. Let me show you how to get a plot here real quick. So let's say I wanted a graph. Let's select our points, and then we go into insert graph, this little chart like that, and there we go. And I see a graph, and we just made that ourselves. The computer would join these with line segments so that it looked a little smoother. But that's pretty cool, right? If I want, I can actually, let's get rid of this beast. Where's delete this keyboard? Cool, get out of there. If I want to keep going, what if I wanted to approximate what's happening at 2? Then I can just select all this and drag this beast down until it, well, no, geez. Selected a little too much. I don't want to do that space. There we go. And so that'll be 0.3, 4, 5, 6, 7, 8, 9, 10, so whatever. Who cares if we overshoot? Awesome. So there's my approximation of the output at 2, which would be this 7.34. And the true value is 7.39. Not bad. Pretty damn good. So if I want this to be way better, I would do something crazy like this. I would say, change that to 0.01. And now let's just take a look at the truth versus the approximation. Let's see, so that's column F versus column H. They look pretty good, but they don't look perfect. But I wouldn't expect this method to be perfect. There's a lot going on in this direction field, but it's not bad. If if I wanted to get a little, let's just see what happens here. I have to get a little crazy. 10,000. How good is that? Well, it's still pretty shitty. I'm just looking at that one there and that two there, and it just looks a little disappointing. But it's also in the hundreds of thousands, so I guess not too bad. I made a second one over here in the back because I was just having my jollies, having fun. And this one is just for this equation right here. So let me show you this one. It's for this differential equation. And that's the most elementary one, probably the one we saw day one. That's just y equals e to the x. So that's the true solution there. And I think I popped a little graph on here. Maybe I deleted it. Yeah, screw it. I don't feel like, but check out how good this one is. Look, I'll delete this column here. Look at those answers. Even with a time step of 0.1, those are amazingly close. That's incredible, right? Quite incredible. And this could be done by hand if we were back in, days of pirates and things like that. I guess there's still pirates. Anyway, I think that's pretty awesome. So my friends, that's it. This is your homework. There are 4 problems in the web work assignment that is now open. Let's start on those. I don't know when they're due, but I bet it's not today. It's probably next Tuesday. Let's check these out and get rolling on this stuff. Immediate application. There's only one Euler's improved method, and they kind of walk you through it again. Yes?
It opens it.
Did it not? What's that?
It opens it.
It opens it too. Well, I really can't tell time anymore. For some reason, I thought that would work. I think I meant one going, so let me fix that. Let's see again. I probably owe you money for being my assistant in all these things. Regis. Oh, it's. That is what I mean. There's that. And if there's anything else, I'll come around and help, but if there's anything else you need help with from your previous things, don't hesitate to ask. Oh, that's weird, it says 1 p.m. Because
It's open?
it's open for you?
Yeah.
Okay.
Yeah, this is.
I'm docking your pay, assistant. Thank you. Does anybody have questions on the existing homework, the written one? Let me know. Happy to consult.